that those energies are actually kind of way out there. For graphene, for example, they are very far away from what you call as the Fermi level, and so they do not contribute. Those electrons do not contribute to the transport, electronic transport and things like that. We talked about that. And what I want to show is that indeed you will get that. So, for example, if you bring those orbitals back, if you bring back these sp orbitals, the way you're going to do that, calculate the entire band structure now, is just as a qualitatively, and then we are going to do it properly for the three-dimensional crystal. So you will have, again, there's a S. Now each electron, or rather each atom site 1 will have one s orbital and 3 p orbitals. So there'll be px, py, and pz, right? We have only considered this till now, right? But now immediately you can see that if I were to consider all of these and this one, then I'll have, in site A I'll have these 4, site B I'll have similarly 4, right? Right? Now we found the band because of this, but now there'll be also bands because of these. And here's the one of the important points. If I, for example, only consider these two, we get 2 bands. We get 2 bands. So each orbital, each atom leads to one band of its own. So if you consider these 3, there'll be basically, 3 more bands. So 3 more bands because of this remote. So basically there'll be 6 more bands. Does that make sense? So totally there'll be 8 bands. And that also happens to be the minimal set of bands for silicon and gallium arsenide and compound semiconductors, and we're going to see that now. And I'm showing here the 8 bands. The dark ones here and the dashed lines, I'll label the dashed line, but the dark ones here are the solid ones, are the ones that are filled with electrons, because again the solid has a finite number of electrons. So each carbon atom comes with 4 electrons, 4 electrons, and therefore the 4 lowest bands will be occupied. So that's the way to look at it, because there are 2 atoms and each contribute 1 electron, so 4 times 2 is 8, and upspin and downspin. So each of these is an allowed state for an electron, and therefore there are 8 electrons for 2 carbon atoms, and the 4 are occupied. And then everything above that is empty. And for graphene, it happens to be at a point which is, as this conical band structure, and it's a Dirac point, right? So we talked about that a little bit. But the bands out here are the ones now, for example, this band, and that band, these are new bands. So you identify this is because of the pz orbital that we already have done, and for that we had an analytical expression. That was the analytical expression. Here's a 2 by 2. You can. But if you add all the others, now that's not quite analytical, but your Mathematica or MATLAB can chug through that. And these are the new bands because of including these other, these 3, right? Ones that have formed the chemical bonds, and then there are all these other ones on the top. So these bands don't quite end here; they continue. This band, for example, this will continue, and So again, yeah, and these are what would be called sigma bonds, sigma bands, and these are the, and the ones that are actually contributing to the conductivity are just composed of the pz orbital, right? That's the idea for the graphene, and also for boron nitride. For boron nitride, this degeneracy here where the 2 bands touch splits, right? And we saw that because the diagonal elements are different. And therefore you get all these other terms. We already saw that at the, okay, let me just, yeah. So for boron nitride, we found that the band gap is 5.8 eV, etc., etc. Does it make sense? Okay. So boron nitride 2 will have all these other bands, which we have neglected just for simplification in the beginning. Okay, so now let's carry this idea over to 3-dimensional semiconductors. And again, I think I want to go through this, though. It's a kind of more of the same, but we want to identify a few things about the 3D semiconductors. Specifically, by the end of the class today, what I want to identify are the symmetries. The question we started out with was, why is it that the optical absorption spectra, if you have a semiconductor, looks a certain way, right? Yeah. And what we'll see is when the photon comes in the light comes in, and it interacts with electrons in the bands. So an electron from a band here can go to a band there only if it satisfies certain rules. These are called selection rules. And we'll see right away that, for example, the reason why compound semiconductors, typically gallium arsenide, gallium nitride, etc., are very, they have very strong light interaction with light. They absorb light very efficiently. They emit light very efficiently. One of the reasons for that is the symmetry of the bands, of the energy states at the bottom of the valence, at the top of the valence band, and the top, bottom of the conduction band. They just are right. So that they are direct band gap. And the symmetries are right. We'll see that the symmetry of this state is S-like, S orbital-like, is isotropic. And this we'll see is P orbital-like. So it's meaning it is elongated in a certain direction. And there's a difference in what you call as the so there's obviously a difference in symmetry. There's also a difference because of that symmetry. There's also a difference in what is called the angular momentum of these two states. And light or photon has an angular momentum of exactly h bar. It's Planck's constant. So photon. So whenever it interacts with something, if it has two states that are separated by an angular momentum of h bar, only then it can change from here to there. Otherwise, it can't do it. So we're going to see that. Well, how does it come about? Yes. Okay. So is that clear? And please stop me if you have any questions anytime. And let me stop here. Any questions? What I did was, I just kind of indicated to you that we had gotten this analytical expression for the band structure by just looking at the 2x2 simplification. I'm just repeating it all over again. But actually, graphene or boron nitride, they have more electrons, they have more bonds. You can bring them back, and it's just that the size of the matrix becomes bigger, and you get the other bands and all that other things. It's just that if you're looking at electronic properties, you won't see the bands that are buried deep inside here, if you're looking at small voltages and all, because all that will happen is the electrons at these very close to the Fermi energy here are going to kind of go up to the high level and conduct, but these will be always buried. It's just like the surface of the ocean. You don't see what's going on at the bottom, right? But then if you come in with a very high energy photon, like an X-ray or something, or a high energy optical photon as well, you can basically kick out those electrons, and then you can see them. That's angle resolved photoelectron spectroscopy, ARPAS, and all these other things. Then you can see these electrons. Otherwise, in transport, typically you won't see them. Okay, so let's see. Any questions before we go to the 3D part? Yeah, please.
Just in the last one, how are K, gamma, and M defined in physics?
I'm going to discuss that. Okay, so these are basically high symmetry points, and for 2D crystals like graphene or boron nitride, as we saw earlier, the K vector or the electron wave vector can have two components, Kx and Ky. In general, I mean, you can take K theta, but generally Kx, Ky is what's used. And in the electron momentum space or K space, if I were to plot, Kx and Ky, then the center of the K space is typically always what's called the gamma point. So center, it'll be the 0, 0 point, and that would be an electron with effectively 0 quasi-momentum, but that means very long wavelength. Wavelength is very long, because 2 pi by wavelength is of the order of the electron momentum or wave vector. The center of the vertices of these. So why did I draw a hexagon? Because if the real space lattice is hexagonal, the momentum space lattice is also hexagonal. This is the first Brillouin zone, and essentially these points are typically called K's and K primes. These are just labels again. I mean, and then the center of it would be called something else. I mean, essentially we'll look at it for the 3D crystal, but this is, for example, for the for 2D crystals, typically gamma point and K prime points are the most important. K and K primes are very important because that's where the minima of the bands occur. I mean the band gaps and all that, right? So the Dirac cone kind of is here, 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 and there are 6 copies of it in this. For 3D compound semiconductors, a lot of the action happens at gamma point in 3D, and then we're going to look at that today. We're going to define the corresponding symmetry points for 3-dimensional crystals. It will be obviously a 3D K space. I mean, gamma point, X point, etc. So we're going to define that today. More questions? Yeah. Yeah. Okay. So good question. I think M is like here. I forget. These are high symmetry points. So I think it's here, but you can check it. Yeah. Right. So you can see, yeah, this is a perpendicular bisector. That is center point. So there are again 6 copies in the here, but then this is divided between 2. So so K points are divided between 3 cells, right? So there are actually 2 in the first units in the first balloon zone. M points are divided between 2, so there are actually 3 of them. Right? So the value degeneracy of M points is 3, and so on. Right? Gamma point is only 1. Right? But gamma has a higher symmetry, as you can see from here, and so on. So, yeah. Okay, so let's move over. Any more questions? Well, if not, let's go over to 3D. And again, as I said, basically we're going to repeat the ideas, but hopefully you'll see a little more detail now of the band structure. And it's really worthwhile going through it because yeah, it would be too bad to go through the whole course without looking at this idea. So yeah. Okay, so 3 dimensions, and I think you have seen that in 3D crystals there can be many crystal structures. The ones we are going to look at in a little detail in this course are the ones that are diamond cubic, such as silicon, germanium, diamond itself, and so on. All the atoms are the same, silicon or germanium or carbon. Okay, so we're looking at group 4. So these are the diamond lattice structure. Then there's the zinc blend. Zinc blend is basically the same crystal structure, except the atoms, nearest neighbors are different. Gallium and arsenic, this is a compound semiconductor now. Just the analog of boron nitride in some sense. So compound semiconductors, what are they? For example, gallium and arsenic is gallium arsenide. Gallium and nitrogen is gallium nitride. Group 3, group 5. So 1 from 3, 1 from 5. And some of those crystals do crystallize in the same form, the zinc blend structure, and some of them go in the word-side structure. This is obviously longer in one direction, and this is it has a hexagonal symmetry. These are cubic symmetries. This is a hexagonal symmetry. And gallium nitride and aluminum nitride and all these are typically, this is the crystal structure for nitrides. So, yeah. And also zinc oxide. Zinc oxide is a group 2, zinc, and oxygen is group 6. So 2,6. This is a 2,6. Sorry, zinc oxide is a 2,6 semiconductor, not a 3,5. Okay. So now again, coming back to this, as you realize, there's let's look at, for simplicity, let's look at, for example, silicon. Silicon, we're gallium arsenide. We're going to look at them at the equal footing. And then only when we calculate the band structure, you realize that, oh, the on-site potentials are different for the two, just like we did for boron nitride and graphene. So we'll break that chemical symmetry. So now you see right away that the bonding, the chemical bonding is such that each atom is bonded to 4 nearest neighbors. This is a face-centered cubic crystal structure. And I'm not spending too much time on these details because I hope you have seen some of these before. So. If you're not comfortable with what is face-centered cubic and what is basis and lattice, please let me know. I can suggest. It's kind of also covered in the prereqs and all that for this course. But if you have any confusion, please let me know about that. So, okay. So we have silicon atoms. Before we go into chemical bonding, let's look at the atomic structure of a silicon atom, for example. And here's silicon atom atomic structure. One atom, not a crystal, just one atom of silicon. And that can obviously exist. If you leave it in atmosphere, it would like to chemically bond to something and not be silicon anymore because it can lower its energy that way. But if you had a pure silicon atom, then we know it's a shell orbital structure. There are 1s2, 2s2, 2p6. This is the inactive part of the electrons, and then there are 4 electrons in the outermost shell, 2 in the s orbital and 2 in the p orbital. But essentially what you have is the highest, or the outermost shell, has 1 s orbital and 3 p orbitals, right? Do you agree? I mean, so py and pz, just like what we had for graphene, boron nitride, all that same thing. Yeah. It has 1 s orbital and 3 p orbitals, and it has 4 electrons out in the outermost shell. The rest of it is basically a noble gas. It's stable, right? And so silicon can accept or give away electrons. So if there was only 1 electron in the outermost shell, it would really like to give it away. That's alkali metal, right? If there were 7, it would really like to get 1, right? And that's a fluorine or one of these halides, right? Very electronegative. They want the electron. But silicon, as you can see, is in the middle, right? It has 4, so it can either give away or it can accept, right? And what it ends up doing the best is obviously it shares, with its 4 electrons with 4 nearest neighbors. So that's what it tries to do. But if it was only, again, a single atom, here are the energies for those for all the electrons. Okay? So 1s, there are 2 electrons, 1s. That's like if you look at vacuum level, this is about 2,000 electron volts below. 2,000, 1,800 or something. It makes sense. I mean, that's how deep that electron energy is, and therefore, if you're making a device where we are only applying 0.5 volts, you're never going to see that electron. It's buried inside. So. But if you come in with an X-ray with 2 kilovolts of energy of a photon, then you can kick this thing out. So that's a core level electron. Similarly, the 2s, 2p, these orbitals are very deep as well, 100 eV, 400 eV, and all that. So as a result, if you look at their electronic structure, so here's the proton of silicon, the nucleus of silicon, positively charged, and then there's vacuum level, and we are looking at, again, the energy is allowed for the electron. What we said was the innermost electron is close to 2 kilo electron volt below the vacuum level. That's okay. And then the next one is 150. So that's somewhere out here, 150, and then there's something else. And then the outermost electrons are about 10 eV or so below the vacuum level. That's so they are kind of very shallow, right? And then that's the atomic structure of silicon. These are how electrons are distributed. And similarly for gallium and arsenic, gallium and nitrogen, you have similar picture. So, and now you bring another silicon atom next to this one. Then we start looking at how does the chemical bonding look. So it starts sharing, right? And I think you will realize right away that if a state is very, very deep, and I have another nucleus here, and again, this has the same structure as, the electrons have the same structure, energy levels as this, but, when you put them together, these are slightly tweaked. I mean, they perturb each other a little bit, move up, down, something like that. There will be a slight change. How much will it change is completely determined by how much is, for example, the electron in this state is very heavily localized. It really never sees what's going on there. There's no overlap of the wave function of this two. Right? If there's no overlap, these energies don't get tweaked much. So the overlap is what perturbs each other. Right? If there's and there's a very deep, and in fact, a very rough estimate is the amount of interaction goes down as e to the power exponentially with this energy. It goes down exponentially with this energy. So as a result, these states do not get perturbed much. So what do we mean? Meaning a silicon atom has 1840 eV energy for the first core level. Silicon crystal will also have very similar. It won't be very different. It won't be tweaked. And then as you go higher, this will be tweaked a little bit, but still is 400 eV below this. So these are the core levels. that don't get tweaked at all. That's why these are not looked at typically. The one that get tweaked most are the ones which are in the top 4 bands, because the barriers are smaller, and then if you have a band here and another band here, so there is quite a bit of overlap or tying together of these two, so they start forming bands. That's the ones we're looking at. That's the justification why we're looking at only the outermost shells, not the inner shells. So yeah. Okay, so we look at so because of that reason, we're going to basically just zone in right away into these 4 orbitals and neglect everything inside. It makes sense? So that's the reason. And then now you have 4 electrons and 4 orbitals that will basically overlap, and we are going to now see by the end of the class today how to calculate this whole thing. Now this is the entire EK diagram, the band structure of silicon. And what we are going to see in the end is, because the minimal repeating unit of silicon crystal or gallium arsenide crystal has one, a silicon in A side and silicon in B side. We'll see that. So there are 2 atoms, again, that repeat. That's the minimal repeating unit for silicon. And it has, again, an S, Px, Py, and Pz. So again, so there are 4 electrons from one side, 4 electrons from the other. So there are a total of 8 electrons, right? And S orbital had a certain energy, p orbitals had certain energies, 3 p orbitals. So we started with S orbital of B, p orbitals of B, p orbitals of A, S orbital of A, right? So you can see there are, 4 energies here, right? 4 energy levels, 4 electrons, 4 energy. So when they mix and form the chemical bonds and all that, how many bands will it form? Basically, if you had 4 states here, 4 states here, the total is 8. So there will be 8 bands in the end, 8 energy levels. You started with 8 energy levels, you'll end with 8 energy levels. I mean, you cannot get a new or a, one less or one more. As a result, there are 8 energy levels here at any k. And what you're going to change, the band structure is basically k is changing from gamma, which is 0, 0, 0, to other points. But at any k, there are 8 energy levels. So there are 8 bands. Here's one band. Here's another. There are 2 here. So that's 4. And then there's 1 here, 1 here, actually 2 here. So there's 4 on top. And so there's 8 bands. And then we have 8 electrons. And electrons always occupy the lowest energies available to them. Right? So always occupy the lowest energies available to them. So 8 electrons will occupy basically the 4 bands at the bottom, and each state can hold 2 up and down spins. So there will be 8. It will fill these 4 bands, and then these will be all empty on the top. Right? So these would be called valence bands. Everything below that and above that is conduction band, and there is a little gap in between them. That's the band gap of the semiconductor. So that's the whole story. Yeah.
So the crystal is symmetric,
yes.
So that the Px, Py, and Pc all have the same, that energy level will remain degenerate, right?
Yes, very good point. Right, very good point. And we are going to look at that. Good point. So yeah. So Px, Py, and Pz, you expect certain amount of degeneracy at this point, and I'm going to look at that.
Yeah. So if they were exactly, would the band be just one on top of the other? It would be the.
Yes,
okay,
exactly right.
Yeah, you won't see.
Absolutely. So this is basically a full-blown band structure which has what is called spin-orbit coupling. What we are going to do, in fact, your assignment problem, this band will be, for example, there will be degeneracies. One band will be exactly on top of each other, another. There will be these degeneracies. And what we'll see is the valence band will have, light hole, heavy hole, light hole and heavy hole, but there will be no split. At k is equal to 0, it will be threefold degenerate. 3 of them will be on top of each other. The moment you add spin is what splits it. And this is called spin orbit splitting, and so on. Spin part we will talk maybe towards later in this course, not right now. So we're going to be non-spin is factor of 2 for us, but there will be quite a bit of degeneracies that we'll see today. And we will track it down to what exactly are those degeneracies. Okay, so just as a again, this is what is called the the approach we are taking is called the tight binding approach, right? Tight binding or sometimes called a linear combination of atomic orbitals, or LCAO approach of band structure. It's the simplest but the most intuitive way of looking at band structure. But there are many others. I mean, there's pseudo-potential method, and you don't have to make any of these approximations in a DFT sort of code, first principles methods that are also very popular these days, and then that is claimed to have the most accuracy. But in terms of understanding physically what is going, what goes into the band structure, this is one of the most illustrative, I feel. So that's why we're covering it in a little bit more detail. So the approach, in tight binding approach, is you start with atoms. You assume that electrons are basically bound to atoms. And when you form a crystal, they start kind of moving around and being delocalized a little bit. Okay? That's one philosophy of looking at electron band structure. The other end of band structure is you start by thinking that electrons are completely free. It's completely free electrons. And then you put it in a periodic lattice, which has this periodic scattering events and all that, periodic potential. And that's another approach of band structure. If you start from that picture, here's, again, I mean, it's a little complicated picture, but do not get too fooled, because the energy of a free electron is basically what you know in classical mechanics. It looks exactly the same. It's momentum squared by twice mass, right? The free electron, meaning free electron means there's no potential. There's no crystal. This electron is free. It's not bound to anything. But momentum in quantum mechanics happens to be, according to de Broglie relation, h bar k. Right? K is the x-axis here. Right? K. A square k square by 2 times mass. So really that is the band structure EK diagram for a free electron. And then you put it in a crystal, and then what happens is you first assume what is called a nearly free electron band structure, where you say that, well, every 5 or every 2 angstroms there is a little blip in potential. I have a atom there, and then so you have a periodicity. You say that I'm going to enforce the symmetry that there are the atoms, but I'm not going to put in their potential yet. The potential has been turned down to 0. This is kind of a qualitative picture of how one gets the electron energies. And then you plot the E is equal to h square k square by 2m. Just plot them. These are all basically just parabolas, but then electron is going along from gamma point. So here's the 3-dimensional k space from gamma to x point. X would be, say, 1 0 0. You're going towards 1 0 0, but then there's a periodicity along x. So what you do is essentially, this is one parabola, and then these are all basically reflected parabolas. There are many of them, and I think this is in your book. And I'm just mentioning that this is an alternate approach. We're not going to go too deep into this, but it's in your book, and please read it up. And then you have another. And another, basically the energies get repeated, because what happens is once you are in a crystal, this becomes k plus or minus 2 pi over a lattice constant times an integer whole squared. That's what the energy becomes. That is really it. And so you have multiple parabolas, and then you can basically just consider the minimal set and reflect everything inside, and you get one band, another band, basically we get all the bands in the first. That's really it. Nothing very fancy about that. We get the same deal with our tight binding too. Okay, so I'm just mentioning this. This is from Rocket, and you can read this. What I'm going to do is the tight binding now. So the basic idea of tight binding, again, we're going to. The reason I'm repeating this for 3D is I want to cover a couple of more topics, especially related to symmetries and all that. And for that, I'm going to actually post this set of slides that were prepared for another course by Professor Rana, and I've used it before. I think he has done, written it up very nicely. So I'll post it on the web. So this is energy bands. So here's the crystal structure. This is face-centered cubic, so these are the lattice points. For all silicon, gallium arsenide, group 4 elemental semiconductors as well as compound semiconductors. And then here's the crystal structure now. The way you build a crystal of silicon is you go to every FCC lattice point. So the face center, here's a center, here's a and then every face center you attach a 2-atom combination, 2 silicons, and then you translate it to there, translate it to there, you get this one, and you start repeating from all phase center sides. Right? You attach that to 2 atom bases, and you repeat it. And you build the whole crystal that way. And then in this picture, as you can see, if you look at this atom, it is bonded to 4 nearest neighbors. There's kind of 2 that way and 2 the other way. So there's 2 like this and 2 like that. That's silicon. It could be silicon, it could be gallium and arsenic. So you can look at the nearest neighbor vectors from, if you consider this to be 0, 0, 0, you're going 1/4 of a lattice constant. So lattice constant is basically this length. It's just convention. You can call whatever you want as a lattice constant. It's just a convention that this is the lattice constant A. When you say what's the lattice constant of silicon, and you hear, well, it's 3 angstroms or whatever, then this is what they're talking about. So this is the distance. And if you look at the body centered, going through the cube from one vertex to the other end diagonally, then this distance between the two is actually a by 4. Root 3 times a by 4. Square root of 3 by a by 4. And the vector joining from here to there, for example, is basically a by 4, 1, 1, 1. 1, 1, 1 direction. And then you'll have 4 other vectors. All you need to do is plop in a negative sign or something like that. You go in this way, that way, that way, and that. There'll be 4, right? And these are the 4 nearest neighbor vectors. I think I've used A instead of N, so in your assignment problem, but that's fine. You should. So remember. So just to summarize, there are 2 basis atoms and 4 nearest neighbors, right? So and we'll see the matrix will be 2 times 4, 8 by 8. So that's what we're going to see now. Same deal, but gallium arsenide and other materials is just that the atoms are different now, right? Silicon and silicon, but now it's gallium. Arsenic and gallium. That's all the difference there is now. Right. Okay. So now what we're going to do is look at the electronic structure. Where are the electrons coming from? So either that or gallium on A side and arsenic on B side. So that would be a compound semiconductor. That's elemental semiconductor, but they have basically 4 orbitals in the outermost shell. Right? And again, we have justified why we are not looking at the deep lying core shells and all that. We're not looking at those. So now we go back and say, well, before chemical bonding, what were the energies of these electrons, right? What were the energies of those electrons before you form the chemical bond? Well, so that we can we basically are going to use that parameters, but there are many experimental ways to measure it, right? So we're just saying that somebody has done an experiment and measured that if the electron was sitting in the s orbital in the gallium side, right? If the electron was sitting in the s orbital, let's say gallium, right? And here's arsenic. Right. Now gallium, as we said, there's a s orbital that is spherically symmetric. And then there's a px orbital, there's a py, and a pz. The electron that came from the s orbital of gallium, right, had a certain energy. Let's call it Es of gallium. It's maybe minus 11 eV, something like that. I don't know yet. We parameterize it. Similarly, there's a s orbital of arsenic, right? S orbital of arsenic. Let's say, so that energy is Es of gallium, Es of arsenic, right? These are the atomic state energies before you form the chemical bond, and so on. So for each orbital, we want to know the energies. So what is the energy of the p orbital in gallium? And now you see p orbitals, if they're atomic states, px orbital will have the same energy as py and pz. Right, if they're atomic states, because the symmetry says that, well, x, y, z are something you chose. Nature didn't choose that, right? I mean, you need to attach coordinates to do your math. Nature doesn't care, right? So px, pi, pz are just, they don't. So their energies are the same. So there are 3 times that and just 1 times that. Right? There are 3. So I'm looking at the energies of this. So this is Es gallium, and these are Ep gallium. Right? 3. Similarly, Es arsenic and Ep arsenic, 3 of them, 3 degenerate, 1, right? Then they combine. So now that's what's written here. so you have 8 orbitals, and you have written down the energies before they form the chemical bond for each of these orbitals. And so at this state, the matrix of yours looks like something like this: Es of A, Ep of gallium, Ep of gallium. There are 3 of them. Right. That's gallium atom. If there was no arsenic, this will be your entire matrix, and there will be zeros everywhere around. Does this make sense? I mean, these are the 4 states of the. Similarly, arsenic, Es of arsenic, Ep of arsenic, Ep of arsenic. So this is really your 8 by 8 Hamiltonian that we are building one by one, and then this is the first row, second row, first column, second column, and so on. So what we look at it now is just change our perspective a little bit and say, what is this diagonal element of my problem? It is that if I have an electron in the gallium s orbital of gallium side, and okay, so basically it is the same energy as the s orbital of the gallium side. This is a diagonal element of a matrix. They're giving you the energies before you form any hopping or bonding or anything. If the electron is sitting in that orbital, that's its energy, right? So without any chemical bonding. Does it make sense? It's the diagonal energy, eigenvalue. And similarly, this would be, you can call it Px of gallium, Py of gallium. And the reason I'm labeling it X, Y, Z now is because the moment you allow for hopping and bonding, then the orientations matter a lot. The angles, the geometry matters very much. And we are going to see why it matters now. So, yeah. But before that, it doesn't matter at all, right? So Pz of gallium. Similarly, this is, just look at this thing here. S of arsenic, Px of arsenic, Py of arsenic, and Pz of arsenic. Okay, so and so on. Let me just write the rest because I'll look at a couple of them as an example. So Px, the same order. Py of gallium. Okay, and then S of arsenic. Py of arsenic, and okay, good. So that's your whole matrix now. And now we're going to use a combination of some intuition and symmetries and all that to argue what are the other elements of here. Because the one thing we know is once I have written down this matrix, I find these eigenvalues. That is my band structure. Right? That much. So essentially, the game is, can you write this down? Right? So that's really the game here. So obviously we made good progress by writing down the diagonal elements first. And as you can see, what will happen is this is going to be this is basically what's called the Hamiltonian or Hamiltonian matrix. And to have real eigenvalues, this is a mathematical theorem that it must be Hermitian. And Hermitian would mean that every element, if I look at 4, 1, 1, 2, 3, fourth row, first element, that must be the complex conjugate of 1, 4. Only then it will have real eigenvalues. Then you guaranteed real eigenvalues. So this must be a complex conjugate of that, and so on. So it basically around the diagonal, you can reflect it, and this number sitting here corresponding to that should be its complex conjugate.
Sorry, I might have missed the book. So what guarantees that it has that permission?
That's a mathematical theorem that has nothing to do with what meaning you're asking, is there's a proof that if this is true, then this Hermitian will only have the eigenvalues are all real. Is that what you're asking?
No. What I'm asking is why do we know that that's Hermitian?
Oh yeah. Oh, good question. So you're saying why should the electron have only real eigenvalues? Or well, okay. So that's the stable state of an electron. Electron can also have imaginary eigenvalues, but then when it tries to exist in that state, it's let me just explain what it's a good question. K dot r. So electron will be a wave, and if it has or you can, let me write it this way: the electron energy dependence on its again, I'm going into this is how the electron energy, electron wave function or the state evolves with time based on its energy. This is how so basically it has a phase, omega, and then it's kind of oscillating with time, right? But and there's an I here. Right? So if it's a real eigenvalue, then you have e to the power I omega t. And so that's basically when it evolves, it can oscillate and all that, right? But if it is imaginary, if the energy is imaginary, the eigenvalue is imaginary, then you see that I times an imaginary will become, you get like e to the power minus some t over tau. So it's what's called an evanescent state. It will only exist for a very small time and it's not stable. You can put it there, but it will go away to one of the real eigenvalues within time tau. That's the meaning. It's called an evanescent state. And if you look at phenomena like electron tunneling, where electron will start from the valence band, go through unallowed or forbidden energies and end up in a conduction band. When it's going through these regions, then it is going through a phase like this, which is the imaginary states. So, so let's look at this problem then, and then again, quantum was not a prereq for this, and I tried to kind of keep the discussion minimal about quantum, but essentially the way you come about with this matrix is one way to look at it is the wave function is really a combination of an electron sitting in an s orbital there times a certain coefficient, unknown coefficient, plus electron sitting in orbital there, and basically there are there are two atoms in the basis, so there are 1 and 2, and each atom has 4 nearest neighbors, so essentially you're kind of repeating that. You're summing over 4 nearest neighbors, and this is the whole wave function, and you kind of project it and all that, and essentially what you end up getting after you project the states and all that is you write your H psi's E psi. I'm just writing the H, I'm not writing all the details for you right now. Yeah. And you get this matrix, and let's now look at how do these elements come about. We have already seen that we have written down the diagonal elements already. It's done. Now let's look at the slightly off diagonal term, and I've asked you to kind of reason it, but I'm going to give you one example. So S and P, S at gallium side and P orbital at gallium side, I'm saying that the matrix element is 0, none. And the reason for that is actually very straightforward. It's completely determined by symmetry. This is symmetry. And the picture of that is on gallium side. Let me picture it this way. I have a s orbital which is spherically symmetric. So the electron wave function looks something like that. And p orbital, px, py, or pz looks something like that. This is 2 lobes. And if you plot the wave functions of those two, so the s orbital will look, in real space, let's say along the x-axis, the s orbital will look spherically symmetric, so it will look something like that. It's actually going to look like some sort of a Gaussian or something like that. I mean, there'll be some nodes and all, but essentially what I'm saying is you mirror reflect it, it's the same. So it's a reflection symmetry. Whereas the p orbital, this orbital has lobe as positive, this has negative signs, so it actually looks something like that. That's S and that's P, and then basically these terms here are terms like so for example, if I look at this term, you have a px on the right side, s orbital vector on the left side, px, okay. And in between you have what's called our Hamiltonian or the crystal potential, the one that's varying periodically. That's what you have. And here, by just looking at it, what you can say is because of this, symmetry of px and s, if I take the two functions that are centered on the same point, which is at the nucleus, no matter what this structure is, you are going to get a 0 because of this symmetry. This is the argument. And in your assignment, you can give me a more stronger argument. I'm going to just leave it here. So because of the symmetry, you're going to get a 0. And as a result, you now get, 12 elements of these are 0. You can justify why px, this is px orbital, and this is py orbital. That I think you can kind of almost see right away. There will be no overlap between the two orbitals. That's already 0. Px, py, pz's, the cross terms are all zeros here. Px, S. So except for the self terms, all these other terms end up being 0 by symmetry. Now obviously the interest is in the terms that are non-zero, and let's look at this one. Okay, so here this term is basically a chemical bond between an s orbital on the gallium side and an s orbital on the arsenic side. They are both isotropic and spherical, but they're not centered at the same point. They are offset by this a by 4, square root of a by 4, nearest neighbor distance. What does that mean? We are now looking at an s orbital here and an s orbital here, right? The overlap between the two. Now you can see that clearly can be an overlap. Let me draw a smaller picture just to show the overlap a little more clearly. So essentially what we're saying is, well, there's a s orbital here, and this is the distance between nearest neighbors, and there's a s orbital here, right? And now you see there's a little spatial overlap between them, and because of that overlap, the energy is actually going to be lowered. The electron can spread out, okay? And this sort of orbital overlap is between s and s, and the lowering of the energy is what we're going to label as VSS. And let me say this is going to be what we call as a sigma bond. It's not a pi bond, but a sigma bond. And I'm going to describe it. So the energy will be lowered by VSS sigma, and what's written here is basically with a negative sign, so it's essentially showing it's lower, VSS of sigma. And there are 4 sites, 4 nearest neighbors, and there's 4 similar bonds. Okay? And again, you will have E phases just like you had for graphene, K dot, A1, which is this vector, A2, A3, A4, A1 plus this plus this. You'll have 4 of these. So that is G0 of K. G0 of K is e to the power K dot first nearest neighbor, second nearest neighbor, third, and fourth. Okay. VSS is the strength of lowering because of this orbital overlap. That is basically this term, except now we are looking at S on gallium side, or sorry, S on arsenic side, and S on gallium side. Okay, without this is the crystal potential. And what I'm saying is tight binding, you kind of use it as a parameter. You're given, minus 10 eV or something like that. You kind of given that, so you can use that. So that's the nearest neighbor. And now let's look at the orbital structure again as to what is sigma pi and why is there a difference. With that, I think we should be able to finalize the rest of the thing. Okay, so oh, sorry. Yeah. Okay, so here we go. So here's the overlap integral. There are 2 s orbitals, and every time anytime you have quantum mechanics, you're looking at orbitals, you can either add them or subtract them. So the 2 linear combinations. So add, subtract. If you add them, meaning if you add this and this, you basically end up getting that. What do I mean by this? So if I take a line along this axis and I plot what is the value of the wave function, the magnitude of the wave function. Here's site A, or gallium site. Here's arsenic site. Here's one wave function. Here's the other s orbital. They can have different heights and all that, but these are the 2. What I'm saying is you can either add them. If you add them, you will end up with something like that, right? So it's maximum in the middle. But if you take this minus that, you will get something like that, right? So, and that's, I think again, is this is the bonding orbital. This is the anti-bonding orbital. Anytime you have a node, that has more energy. Anytime you have a node, right? So if you have a node, this has high energy. That's called the anti-bonding, and then so if you have chemical bonds like this, this is called SS, and sigma bond is what we show here. And it's an energy. That's all I'm trying to say. In this matrix, it ends up being minus VSS sigma, and there's this Z0 of K, which I'm saying is because of the nearest neighbors. There are 4 of such bonds. Just like for graphene, you had 3. Here you have 4. Now for the p orbitals, there's a little more structure because s orbitals have spherical symmetry, so it makes life a little simple. But p orbitals do not have spherical symmetry. Right? So now p orbitals, you can bond them in two ways. You can bond them end to end. Right? This is a px. Let's say this is the x-axis. Here's a px. Here's a px on the two sides. It makes sense. So if I have gallium and arsenic, here's a px. Here's another px. That's one way to chemically bond the two. There's one possibility of chemical bonding. Right? And that bonding is called the sigma bonding when they are kind of end to end or lined up like that. Right? So, and then that energy again will form antibonding and bonding, and the lower energy will be the VPP sigma for us. But the p orbital can also do another kind of bonding, where it's the lobes are like this, and then there's a pz orbital, right, or a py orbital for both. Right? I'm looking at x, y, and z. Right? So this is a pz orbital, and that's a pz orbital. Now you see the chemical bond is different, right? And it's kind of end. Does it make sense? I mean, the lobes are connecting to each other very differently, right? And that is what's called the pi bond here, right? So the pi bond where you connect, and so when you add, again, you get this. When you subtract, you get this. You see that? I mean, it formed like a quadrupole of. These are signs of the wave function. It's not really charged, but the sign of the wave function. Here, this is more like a dipole. Right? This is a quadrupole, this is a dipole. So, yeah. So this is another energy scale, PP with pi orbitals and VPP with sigma orbitals. So the two different energy scales. Here's an energy scale. Right? And with this, so these are basically going to have different values, and I think there were, I've given you some numbers in your assignment, so you can just play with that. And you will see that one of these energies is, for example, if you have a node in the middle, the energy is always higher. So if you're given only one energy for PP sigma, you're given the lower energy typically. Okay. Now there's only one more thing we need to look at the entire tight binding structure, and that is if things are not that nicely ordered. What does that mean? It means that what if I had an orbital of p or s or anything like that? So for example, what if I had an orbital of p that's like this here, but another one which is kind of over there but at an angle? It's not quite 90 or what if it's at an angle? And as you know, silicon, gallium arsenide, there are all these covalent bonds that are at 104 degrees or something like that. There are specific angles along certain directions. Or what if I had, maybe do the simpler picture here. What if I had a s orbital which is spherically symmetric? It doesn't care about angles. And there's a p orbital out there, right? Now that p orbital, you can now draw a bisector here, okay? And you can see that the p orbital, let's say it is kind of vertical here along the z-axis. Okay? And you can see now that you can decompose it into one that is along this and along that. And decompose it into two. Is that clear? I mean, so you can always decompose into two. And maybe you can tell me, p orbitals always have opposite signs for the lobes, wave functions have opposite signs. Which one will form a chemical bond with the s orbital? Meaning, which one will have energy that will be different or something like that? Yeah, so you see along this axis, you will have a little orbital that will look like that, and that part can kind of combine with that, and you will get something non-zero. But if you look at this one, with that, it basically, if I bring it over here, you have an overlap, but part of it is positive, the other is negative. It'll cancel out. You get a zero. That makes sense. So you can turn these angles, and so as a result, you have these extra terms. So s and p. So if you have, so we're looking at gallium atom here and an arsenic atom there, and we're looking at the p orbital of that. For example, s here and p there. So we're looking at those terms now. Does it make sense? S on the gallium, but p on the arsenic. Right? So we're looking at those, and this is the chemical structure of it. And this is where the electrons are coming from. And so we're asking what are the energies? Well, we need to find those terms and then solve the whole Hamilton to find the energy. So we basically, this works out actually very beautifully. You can take the orbital and just take its geometrical projection, just cosine theta. If you know that angle, if you know theta, just take VSP. So this is SP sigma, SP. We just saw that will be non-zero, right? And you project this bond, this essentially a dipole in some sense, at angle theta, make it cosine theta. Turn it at that angle, sin theta. And this can be shown rigorously. I mean, I think I'm not doing that here. And then the 90-degree part will give you nothing because of the symmetry again. So it's positive. And similarly, if you have P and P, you can see that end-to-end bonding will give you PP sigma. Just going back, end-to-end bonding gives you VPP sigma. But perpendicular bonding, this is allowed. This is not disallowed, right? If it's only if this was S and that is a perpendicular, then it's not allowed, right? But if both are P, it's allowed. And you get VPP pi because of that, VPP pi, right? But now this has been turned by sine square. So so both orbitals are turned, so the cosine square and a sine square. Does this make sense? So those are the energies that you end up. And this is the terms that you have here in each one of these. So depending upon which direction you're going, 1, 1, 1 or 1 minus 1, 1, the angles will be slightly different, right? Right. So you just have to take care of those, and that part you have to explain in your assignment. This is why is this 1/3? Why is that 2/3 and all that? All of them come from like cosine square 60 or something like that. Okay. Okay, good. And these energies are, I'm saying that it's provided you understand what they are. So we're going to go with that now. And sorry, it looks a little messy, but essentially as a result, what happens is this term here, this term is V1 times G1. V1 is 1/3, 1 over square root of 3 SP sigma, and you can kind of, it's S and P orbital and all that. And then you have G1. G1 is this, and you can show why it should be like that. There's 2 negative signs and 2 positive signs in that phase factor. Okay. And then it's mostly others are zeros, and this part is basically all complex conjugates of that part. Right? And that's your whole Hamiltonian. And what I want to do for the rest of 10 minutes that I have here is actually, let me just stop. I know there might be some questions. If there are any questions, just work it out by yourself once, because it's only so much you can learn by listening to me. But just once you do it yourself, it'll be pretty clear. And that's it. I mean, there's no other fancy things here. And then you get your whole matrix. You get all these terms. And basically, for silicon, germanium, or gallium arsenide, you're given. You can find these numbers from literature or whatever, and I've given you for the assignment. Plug them in, diagonalize it, and you get your whole band structure, EK diagram. Okay, so now for the EK diagram, the plotting it, coming back to your question again, what are these points, right? So K, so as we saw G0, K, each of these terms here have this G term, G0, K, for example, is e to the power I, K dot A1 or N1, nearest neighbors, plus e to the power I, K dot A2, plus, there are 2 more, right? And each of these K's is Kx, comma, Ky, comma, Kz. Right? So when you look at the Hamiltonian and say, well, Mathematica or MATLAB, find me the eigenvalues, it's going to first ask you, well, tell me your Kx, Ky, Kz. Only then I can tell you the eigenvalue, right? Because this is a variable. Everything else is a constant. All these V terms, these are all constant. Only K is a variable. Right? And as you change the K, this is what's going on. So at K, when Kx, Ky, and Kz are 0, you have 1 here. You have you can see this, and these numbers are the degeneracies. It asks, are the bands degenerate? In this picture, this band it's twofold degenerate. There are 2 of them on top of each other. And so you have 2 plus 1, that's 3. So you have 8. And you must have 8. It's an 8 by 8 matrix, 8 eigenvalues for each K, right? And as you change the K, you can see the things are evolving, right? Things are evolving. Right? One very nice way to picturize it is you can go back and say, I'm going to just turn off the entire crystal and make all these V's 0, right? Make all the V's 0, because all these V's in these off-diagonal terms are what are the hopping terms, right? If you make all the hopping terms 0, you should recover all your diagonal terms, and that's trivial. If these are 0, you get, right? And therefore, these energies should be essentially related to the diagonal terms, right? At K is equal to 0, should be related to that. And the origin of those states at K is equal to 0, all the symmetries and all that are actually the same as the symmetries of the orbitals it came from. It was dominated by s orbital, it will be a spherically symmetric state. It's dominated by p orbitals, it will be linearly elongated along certain direction and all that sort of thing. Okay, so gamma point is k is equal to 0, 0, 0. Is the center of this k space, kx, y, kz, so 0, 0, 0. If you go along the face centers of any of these axes, this is, remember, face-centered cubic crystal. So those are the x. The directions are called x directions. 1, 0, 0, going from 0, 0, 0 to 1, 0, 0. This is a gamma to x. You go from 0, 0, 0 to 1, 1, 1. Now that's the diagonal, body diagonal, right? That's called gamma to L. This is a L point. This is basically high symmetry points and all kinds. So gamma to L, gamma to X. K, as you can see, is like 1, 1, 0, right? There's no Z, but X. So all these other, so these are all, you can go in. So the directions are equivalent, meaning it's a cubic crystal. So you go from here to there, or in 0, 1, 0, 0, or 0, 1, 0. It's the same, symmetric, two directions. So what we'll see is actually for silicon, the minima of conduction band occurs actually off along the gamma x direction at 80% out from the center of the Brillouin zone and all that. Gallium arsenide, the minima occurs exactly at gamma point. Exactly at gamma point is the minimum of one of the bands.
So should we choose that path?
You can choose anything you want. Exactly, it's up to you. But oh yeah, I was trying to think. I wanted to say something here, and what I wanted to say is, in your assignment, I've asked you to plot it along certain directions, right? I've asked you go from L to gamma to X to K to this, right? So, for example, for that, what you have to do is look at this band structure, right? So we start from L. So essentially, you can start from here. What does that mean? Start from here. Find the eigenvalues for k is equal to 1, 1, 1, right? And then go from L to gamma, right? What does it mean? You scale it down from 1, 1, 1 to 0, 0, 0, but don't change the ratios of it. Does that make sense? So you go from 1, 1, 1, you're walking along the diagonal along this dashed line to gamma point. So basically, at some point in between, it'll be half, half, half. It'll be 0.2, 0.2, 0.2. It won't be 0.2, 0.2, 0.4, because then you have stepped out of that line. So this is just a high symmetry point, because you see, you can think of this, you look at this structure, and you kind of, if you look at the diagonal and you rotate it by 60 degrees, it will always come back to itself. So it has a very interesting hexagonal symmetry around that 1, 1, 1 axis, for example. So as a result, the wave functions there will have that symmetry too. You kind of rotate it, operate on it by a 60-degree rotation, it will come back to itself, and that sort of thing. So it has these properties. Okay, so that's L to gamma. Then you can walk from gamma to X. So you go along, you turn this part off, increase this now 1, 0. So essentially, these are just axes. All you're doing is finding the eigenvalues of this for different k values, and these are just different range, things of k. So you can go through any path. You start from X, go to gamma, maybe go to X, go to W or whatever, come back to X, and you get a thing that comes back on itself, something like that. So that's what I've asked you to plot. You can do that. Okay, so one of the things I wanted to say, don't have much time, but I'll just mention this, and we'll finish this discussion in the next class. One of the things is very important that comes out from here is you have these energies, so you can plug it and find all this stuff in. And for gallium arsenide, again, you have 8 electrons for two atoms. 4 electrons per atom, and then you have this band filled, that band filled, and that band filled. Okay, but that band has 2, so there's 2 plus 1 plus 1 is 4. 4 times 2 each is 2. So these bands are all filled. These are valence bands. That's conduction bands. Okay. What we want to do for the next couple of minutes is look at the symmetries of these k is equal to 0 states. The k is equal to 0 state is very easy to find out, because you just put k is equal to 0 in this matrix, right? Just put k is equal to 0, and you look at what happens then. You see that G0, all the k's go 0, so this thing becomes 4. 1 plus 1 plus 1 is 4. But all other g's become 0, because there are 2 positives and 2 negative signs. So it's 1 plus 1 minus 1 minus 1. So what happens is, you see the structure of this is G0s are in the diagonal on this side, on this side, and everything else goes to 0, right? If you put k is equal to 0. Does it make sense? So essentially what you have is a diagonal here, 4 by 4 diagonal, a 4 by 4 diagonal there. Right? That matrix, I think you can go back and just do a little rearrangement. That's trivial to diagonalize. You don't have to do any, you don't have to ask mathematically, you can do it by hand. And what happens is that becomes a 2 by 2 in the end. So it's just a 2 by 2, it's a parallelogram. And the end result of that is when you diagonalize that, so yeah, I just mentioned that. So you get 2 bands, which have the, okay, so you obviously still get 8, but you have 8 by 8. But what you get is the two of the eigenvalues are specifically the one at the bottom of the conduction band and the one deep down here. Those two. Their energies are basically just energy of s orbital in gallium and s orbital in arsenic. You remember this we did for graphene. Same deal. Different. Sorry, not graphene, but boron nitride. We did for boron nitride. The two are different. And then what you have is VSS sigma. This is because s and s orbitals did overlap. They term this because only these diagonal terms have survived, right? And then you have 4 times that squared. So essentially you have a split. Therefore, from here to there, that energy separation is 8 VSS sigma. So if you could experimentally measure this energy and that energy by kicking out one from here or there or something like that, you got your VSS sigma experimentally. Does this make sense? Okay, so those are the 2 states. What is very important is you see their energy is completely composed of s orbitals. There's no p orbitals at all. What does that mean? It means that at that energy, if I look at the wave function of the electron, from gallium to arsenic, it looks, something like this. Just, S, 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 S. Spherically symmetric around every site. So, every site. And then what we'll see now is, so that one and that one. And remember, this is occupied, it is deep down. Typically, you don't do much of electronics or photonics with that. And this is conduction band minima. You do a lot with that. And it's a s orbital. Its symmetry is spherically symmetric around every atomic site. But it's a block wave, meaning essentially its wave function looks something like this. It's going like that. And the second thing is, if you look at all the other eigenvalues, so there are 2 which we found, that this and that. Yeah? And then there are 6 left, right? And I think you can see 6. There is 3 here, 2 plus 1 here, and then 3 there. And all 6 of them, again, is the other part. So essentially, they are composed completely of p orbitals. No s orbital contribution for them. And you can see that basically the s orbital part gives you 1, and the s orbital part will give you 1, and then the p orbital parts will give you 6. Okay. And the p orbital states have obviously states that would look does that make sense? There's a node and all that stuff in between. The p orbital, right? And you can see intrinsically they have different symmetries. And as a result of this, what we'll see in the next class, again, I hope you can see that. And then there's a V1 here, because this element here is like is V1 times some G here, right? So that's the element there. So if you can measure the separation between this and that, you got your 8 times V1. So it's a separation, right? Experimentally measure it, right? And finally, those have the p orbital symmetries. These have the s orbital symmetries. And very interestingly, as you know, already we know that this is filled and that's empty. So if I were to shine a photon into this material, the photons will try to kick out electrons from these filled bands into the empty bands, right? And the one where you start the absorption is a very strong transition, which we had talked about, is what's what you call as the band gap or the band edge of the transition, right? Sorry, I think I'm done here. So when you start increasing the energy of the photon, and then you at some point you hit this maxima, which is like p-like orbitals, to this minima, which is empty, and it's a s-like orbital. That's when you hit it, and that's this huge jump. And the reason it can do it is because the photon that comes in has an angular momentum of exactly h bar, and what we can show later in the course is if you go from a p orbital to an s orbital, the difference in angular momentum is exactly h bar. And that's why it is allowed. It's allowed transition from here to there. And going by that argument, if you go to the higher p conduction band orbital here, that's also p, as we just saw. This is p, that's p. This transition will not be allowed. Optical, it's not allowed. Okay, good. So let's stop here, and next class we'll kind of continue from here. And please get started on the assignment. I think I gave you all the answers, so please just go forward and finish it. And we meet on Thursday.